Welcome everyone to today's video. Um, Today we are going to start off with a new topic in the chapter of fluid mechanics. So that is Stokes' law. So Stokes' law is basically associated with what we have been doing, studying in the previous video. Um, so we were talking about viscosity. Viscosity means that when two layers of liquid they are rubbing against each other, so there is a friction force involved because of interaction of particles. So to overcome that force, we have to apply a force F, uh, whose which becomes equal to the viscous force. Uh, so Stokes' law is about that force only. That force acts in two ways uh, on a body um, in a liquid. Earlier, we were only talking about there is a liquid, so as liquid, they glide over each other, the layers, so there is a force. In case of a body, for example, let's take a spherical body. So we want to simplify our case, okay? So in case of simple, for matlab, less complex cases, we can take a body which is spherical. That means it will have some radius r and other characteristics. It will have mass and whatever. Now, when a body is going through some liquid like this, what qualities of liquid are pertinent in that scenario? So you would say for a liquid, we have just studied viscosity. So yes, viscosity is something which is required. And what else? Uh, then we require what would be its what is the speed of the body with which it's moving? So that is also correct. And the speed with which the body is moving, that would also be involved. So let's say the body is moving in this forward upward direction in this liquid of viscosity eta. So Stokes' law says that there is a viscous force acting on this body in this downward direction, which I have just drawn, which is opposite to the velocity of the body. The value of this force we can calculate. Uh, the reason why this force acts is twofold. So, first being simply the layers of the liquid are rubbing against the body. So, as they are rubbing against the body, they produce friction force. So, that force is basically producing some heat. So, that means that okay, we have to supply some kind of energy, and that is supplied by that force. Second reasoning is very interesting one. We say that okay, there is a vacuum that is created, and there are two vacuums which are created. If you can imagine this figure, sorry, there is a viscous force here, and there is a vacuum here. So, because of the flow of the liquid with respect to this body, the streamlines are formed in this way, because of which there is a formation of vacuum beneath the bodies as it is moving upward. So this also creates a pressure difference, which contributes to the viscous force. So that means that viscous force acts because of two reasons. Reason number one, because of simple rubbing of these streamlines against this body. Okay, as a bowler is bowling uh, in air. For example, a favorite bowler nowadays is Jasprit Bumrah. So as Jasprit Bumrah is bowling to, let's say, a batsman, let's say he's bowling to Surya Kumar Yadav. So if the ball, he wants to swing the ball. So how would he bowl? He would produce some revolutions. So when he's bowling the ball, there is a viscous force acting on that ball, which is just opposite to the velocity of the ball. So this acts irrespective of whatever swing or spin is given to the ball. If the rotation of the ball is in clockwise direction, even then this viscous force is in this direction. If the rotation of the ball is in clockwise direction, even then the viscous force is in this direction. There would be some additional forces generated because of the rotation of the ball. That is the Magnus effect. Uh, but for our case only, let us see that okay, because of the linear motion of the ball, what is the force acting? So that force is the given by Stokes law. So F is equal to 6 pi r eta v. So pretty typical formula. And this F force is called viscous force. This is called the viscous force. R is the radius of the object. Eta is called the coefficient of viscosity. And V is the velocity. So these are like relatively uh, easier terms to remember. That if we have a body which is moving with the speed v in a fluid of coefficient of viscosity eta, so this F viscous force equal to this will act. And last question which you can think is how did we came up about this formula? So this is entirely an experimental formula. We have determined that this viscous force it depends upon speed and the geometrical features of the body. In this case, the geometrical feature is R. So it will depend upon R, V, and eta naturally. So this factor 6 pi, it can be determined using experimental observations. We can throw a ball and what is its value, what is the viscous force it is experiencing, using that we have obtained. But also we can obtain using mathematical calculations. We can do some concrete calculations regarding the flow of the fluid, like how the fluid is flowing, what is the force exerted by fluid, and using like maths which is above and beyond the scope of even UG students, we can derive this. But for our purpose, only this much is uh, understanding this much is more than enough. But still, we must think that what if the body was a cube instead of a sphere? Let's say uh, you start bowling with a cube. Rubik's cube you are bowling. The Rubik's cube will experience what viscous force? It is also an object. It can also go in some kind of atmosphere. For example, you want to study that case there is a uh, let's say you have sent the lunar module to orbit the moon. Now, after orbiting the moon, it is coming back to Earth. So when it will enter Earth atmosphere, how will the viscous force act on that cubical module? If you can imagine, it is of cubical shape. So it's not matlab, out of the realm of reality to matlab, to guess those forces. So let's move. So next we want to do three questions today. First question is on the basis of viscous forces only. So it's a fun question. You will like it. Basically, there is a table tennis ball, and that table tennis ball is being pushed inside a
uh, pool of water. Okay, let's say there were two friends who were playing some table tennis or ping pong, somewhere it's called, and that ball it dropped in the pool. So it won't naturally sink inside the pool, right? There would be some other, let's say, a dog came along and dog started pulling that uh, ping pong ball beneath it using his teeth. He grabbed the ball and you know, he's basically playing around with it. So the question is that what is the work done in taking that ball to a depth edge inside the pool? Okay, so we are given that the mass of the ball is some I think 22 by 7 into 10 to the power minus 3 kg, and the radius of the ball is some 3 by 2 into 10 to the power minus 3 meters, somewhat like that. I'll tell you the question because like imagination you can do anything, but exact question is there's a table tennis ball of radius this much and mass this much. It is slowly pushed down a swimming pool to a depth this much, 0 0.7 meters below the water surface and then released. Question is that when it is released, you would have seen that you would have imagined that the ball will come up to the surface and will bounce above, right? Or it will plop up the pool. Question is that with what speed it will reach this surface and till what height it will bounce above the surface of the pool, capital H. So it's a pretty fun thing, right? You can, instead of a ping pong ball, you could have, let's say, a volleyball, and you guys are playing volleyball or whatnot. There are options, okay, and more than one options are correct. First option is work done in pushing the ball is this much. If we neglect the viscous force in water, then the speed is 7 meters per second. If we neglect the viscous force in water, then the height h is 1.4 meters. And there is a question, fourth part as well. That I'll tell you later. So first of all, we have to work out what is the work done. So how do you calculate the work done? Work done we calculate using forces. We multiply forces with displacement. So what are the forces acting on this ping pong ball? That is the first thing that is the thing which we should start with. Okay, what are the number of forces? Then writing those forces. So first force is, let's say, gravitational force only. That is mg only. So mg is acting. Next, buoyant force is there. So I have labeled that as fb. What is the value of buoyant force? It is v rho g. That's it. V is the volume of the ball. Rho is density of water, which is given by the way, and g is also given as 10 meter per second square. So all these things are given. Rho is given, g is given. Although density of water you would have known, right? But sometimes it is given, so that you would only take those values which are given to you. G is there and pi is also there. So definitely when I'm pushing the ball downwards, right? So when I'm pushing the ball downward in the pool, so this will be more than the band force acting on the ball, and the gravitational force acting is supporting me. It is helping me take downward. So the net force which I have to supply is just so as to take it down with no net force acting. So I'll repeat that once again. When I'm pushing the ball down, I want only that much force which just keeps the net force on this ping pong ball zero. So that is essential because we do not want any speed uh, gain in the ping pong ball. If the ball is gaining speed, that means we are supplying additional kinetic energy. Whatever extra energy which I am supplying, that is going in kinetic energy. So then the question will become, okay, what is the extra energy which I am supplying? And what is that velocity which I am getting? So that is not there in this question. It is only given that, okay, what is the work done in pushing the ball? So when I'm saying that is only the work done in pushing the ball, that means that we are not concerned what is the kinetic energy involved in the situation. Only that we are pushing the ball downwards. Simple and that. So net force is band force minus gravitational force. So this band force is volume of the ball. So that is 4 by 3 pi 3 by 2 10 to the power minus 3 cube density of water 10 to the power 3 into g minus mg. Mass of the ball is given to us as 22 by 7 into g. So this is the net force acting. This value comes out to be 0.11 newtons. So I'm writing this expression directly. I hope it is visible that this is 0.11 Newton because I have already pre-done this calculation. So this calculation, if you do it, its value is going coming out to be 0.11 Newton only. So, but what is the next step that we have to guess? That is the important part. Okay. Uh, so next step is finding the work done. So to find the work done by this force is simply the force into displacement. And that is 0.11 Newton into the d distance which the ping pong ball has been pushed down in the pool. So that is 0.7. So this value is some 0.077 joules. So this is the option number one. Next. Next idea is the speed v with which the ball emerges out of the pool if we neglect the viscous force. Okay. So would you be saying that, okay, sir, you have just taught me viscous force, right? But why is the option saying do not take viscous force? So I'll tell you. Basically, viscous force, when it acts on a body, it is a variable force. It's a very pretty looking formula. They would have liked it. 6 pi r eta v, right? 6 pi it would be difficult to remember, I know. But with practice, you'll be able to get. But 6 pi r eta v, that v is the thing which is like not very easy mathematically. The force F, when a force F is proportional to some kind of speed, then it is called a non-conservative force. Not only is a non-conservative force, it's a variable force. So because of which the work done by this force is changes with every dx displacement we have taken. And not only it is changing with displacement, it is also changing with speed. So to calculate the work done because of such a force, it is not a straightforward thing. Let alone finding the kinetic energy or finding the motion. But still it can be done. We can do it. Like it is there. That's why the formula is there. But the point is that when we calculate it, when we find out through it, we will get some kind of speed. Okay. Now you can imagine that what kind of speed that could be. Matlab, if there is a body which is going inside a liquid, would the speed of the ball increase or decrease? In this case, as the uh, ping pong ball is, when it is the ball, ping pong ball has been released. When the ball will be going up, would its speed increase? So you would be saying yes, it would be increasing first, right? Because its speed is zero. So that means buoyant force is taking upwards. But as the buoyant force starts taking it upwards, there will be viscous force acting as well. And that increases with speed. So at some point, the viscous force is not as significant. But when it becomes significant, it will be able to balance all the forces. That means it has the capability to become equal to F. That was the force which was pushing it downwards. So it slowly grows to F. So instead of imagining what motion it is, first we imagine what is the force it go through. Then we say that okay, this is the force it can grow up till. Then we will say that okay, it will start gaining some speed, and after one point, it won't gain any further speed. It will just reach a speed where net force is zero. So the question does not want to think us in that way. It wants to straight up say that okay, there is no viscous force. Just think without it. What would happen then? That is the easier scenario. Simply whatever energy which we have supplied, it will come back. If that non-conservative force was acting, in that case, an energy would have been gone away. But since only conservative forces are acting, band force can be taken as a conservative force in this case, as it is as a constant force. So it will return all its energy. So that means whatever work we have done, it will come back to us in form of kinetic energy. And this is the speed, maximum speed it will reach. Not only it will be the maximum speed, it will be the speed it will reach when it is coming to the surface. So this value is equal to half into mass 22 by 7. Now take carefully here, we have to take the mass of the uh, ping pong ball into 10 to the power minus 3 into v square. So again, after we calculate this, this value comes out to be v7 meters per second. Next option we have, if we neglect the viscous force in water, what is the height h it will grow up to? So we have to simply say v squared is equal to 2gh. After coming out of the water, it will reach some height h. So v squared is equal to 2gh. So what will be the value of h? So this value of h it is saying should be 1.4. But as we calculate, it won't be coming out to be 1.4. If we put the value, this is 49 equal to 20 into h. So this h comes out to be some 2.45 meters. So this h is 2.45. So this is not matching our options. That means our option C is wrong. We have option D now, which I was telling. So now it is saying you have to take the scenario which we were stating earlier, that is of the viscous force. But it is only saying that the ratio of the net force, excluding the viscous force, to the maximum viscous force in water is. So it is not saying that we calculate the whole velocity, what is the velocity of the body, maximum velocity, what it's going to reach. It's not saying that. It's saying that what is the viscous force. What is the viscous force and what is the net force? Net force we already know. Net force was some 0.11 newtons, right? This we calculated. So you have to divide this with the maximum force which can act on the body because of its viscosity. So this maximum force, we will say that the maximum speed with which it can reach. So as it is going upward, again, you would see me scratch my head, even though we already knew that how is the motion going to be? It's going to speed up, then it's going to get constant. But still, um, is it going to reach that speed or not? So the answer is that if I release that body from that particular instant, right? At that particular instant, if we are releasing, then it is going to certainly gain some speed. But as viscous force is acting, uh, there would be some work done by viscous force as well, right? So in let's say the depth was very high. Depth was so much that the body was able to reach that speed of 7 meter per second, right? There we are saying that the viscous force is able to balance the net force acting on the body. So in that case, what we'll say, if the viscous force is able to balance the net force, then in that case, this ratio would have been one only. But if it is able to reach that particular force and maximum force, then what will be the case? We'll say this is 6 pi r eta into the velocity. So that is some 7 meters per second into 0.11 newtons. So in effect, what it is saying is that although you take up the body up till that particular point, just calculate what is the viscous force acting at that point. So this value is 0.11 is 6 into 22 by 7 into r. R is the radius of the sphere. That is 3 by 2 into 10 to the power minus 3 into again 10 to the power minus 3 coefficient of viscosity into 7. So again, so this value, let's see what it is coming out to be. So this is 1 by 2 into 2 into 3 into this 3, that would be 9 into 10 to the power 4. So this is some, and there would be one more 2 as well. Yes, there would be one more 2. 1, 2 is getting cancelled. Yeah, so this is coming out to be this much only, I think. 2 by 2 into 10 to the power 4 by 9. So this is 10 to the power 4 by 9 ratio. So basically this option is not correct. Next we have another new question. We have a bubble. So all the bubbles we haven't studied yet, but still we can discuss the question. So again, this is a question which has a bubble and it also involves some concepts of thermodynamics. So Uh, Basically, we know that inside a bubble there is something called excess pressure. Only that much concept is used. And mainly the question belongs to the realm of thermodynamics. So, from the part of fluid mechanics, what we need to know is that if there is a bubble and that bubble is basically a soap layer. So when there is a soap layer and it is formed in some spherical shape, there is some extra pressure inside that bubble because of the shape of the bubble. So it's spherical in shape and it has two layers. So the layer of the bubble it is maintaining itself, maintaining its shape by the help of surface tension because the pressure inside is more. It needs something to hold all the air together. So that is possible using surface tension. You can imagine that there is some kind of a spherical shape, and on is that sphere you can imagine a circle. So on that circle, the surface tension is acting along the tangent to the circle in such a way that they are pulling the particles downward, and the air pressure inside is trying to push the particles outward. So that is how the whole bubble remains in equilibrium. So, what is that extra pressure inside a bubble? So that is its value is some 4s by r, where s is surface tension, and that is the extra pressure. The question is that if there is a bubble, in that bubble uh, we have put some air and or whatever we have some ideal gas whose ratio of specific heat is 5 by 3, so matching that of air. So gamma is equal to 5 by 3, surface tension is some s. So the bubble is exposed to the atmosphere and it retains its shape. So obviously bubble has to be in atmosphere only. So it's saying that atmospheric pressure itself is changing. So inside a bubble, what is the extra pressure? Or what is the net pressure basically? Extra pressure I already told it is 4s by r. S is the surface tension and r is the radius of the bubble. So this is the situation. We have some ideal gas whose inside this bubble at some temperature T1. So the question is saying that okay, at T1 temperature, pressure inside the bubble is P1. Uh, so okay, that is there. Okay, now the bubble is going to expand. It's going to reach some radius. Going to reach some radius R2. So as it has reached some radius R2, we'll say that okay, now the pressure is 4s by R2 PA2. So this expansion has happened without any external heat. Okay, so when there is no help of external heat uh, used in expansion, uh, so this is called a adiabatic process. So in such kind of process, in an adiabatic process, we have several equations which help us. Basically, these equations give us relation of pressure and temperature, which are involved here. The pressure temperature equation we will definitely use, and also pressure volume equation. So one of the nifty equations which we have is PV to the power gamma as constant. So all that is very sweet and rosy, right? You are learning a lot of equations, but what is the physical significance, right? So regarding bubbles, I have already told that there is some extra pressure because of the soap membrane. Okay, so that extra pressure is this 4s by r1. But what is this process involved? So this process is this gas has basically either expanded or contracted on its own. So is possible because of some external pressure, atmospheric pressure, it has happened, but the cause is not important. What is important is what are the how the process has taken place, so how pressure and volume will change. Okay, so this PV to the power gamma is constant. We have one more equation, P P to the power 1 upon gamma minus 1. This is also a constant. So this is also a useful equation. So yes, so we have multiple statements which we have to check about. Right. All right. So the first equation is the process which is involved is what I have said. There is no heat passage through the bubble membrane. So what is the relation of pressure and temperature? So that we can guess the relation of pressure and temperature we can find using this relation Tp to the power 1 upon gamma minus 1 is a constant. The value of gamma I have erased, but it was 5 by 3. So let's just put that value. So this is T1. 3 by 5 minus 1 is equal to T2 P2 max. So this value T1 into P1 to power minus 2 by 5 is equal to T2 P to the power minus 2 upon 5. So this means T1 upon T2 is equal to P2 upon P1 to the power minus 2 by 5, or we can say T1 upon T2 to the power minus 5 by 2 is equal to this. So this implies T2 by T1 is equal to the power 5 by 2 is equal to P2, which was some PA2 plus 4s upon R2 plus PA1 plus 4s upon R1. So this is option D, one of the options of the thing. So this is correct. Next, we have if the process is such that there is exchange of heat, but there is no change in temperature. So this is one of the easier ones. When there is no change in temperature, we use PV is equal to constant. So P into V is a constant. So as P into V is a constant, we know that we can again plug on those values only, that pressure P1 and P2 is equal to R2 cube upon R1 cube. So this value P1 is simply PA1 plus 4s upon R1 plus PA2 plus 4s upon R2. It is equal to R2 upon R1 to the power 3. So this is option number C. So this is also correct. There's one more option which we have to discuss. If the surface of the bubble is a perfect heat insulator, then the total energy of the bubble, including the surface energy, does not change with the external atmospheric pressure. So that is saying that the internal energy of the gas inside the bubble will not change if there is no heat supplied to the system. So this is a common misconception, right? No heat is supplied, no temperature change. Like it appeals to the uh, uh, un, unknown mind that only. But in a adiabatic process, we are saying there is no heat exchange. So how is the gas expanding? When the gas is expanding, basically it is the particles of the molecules are going away from each other, right? So as they are going away from each other, that means that some work has been done, some expansion has taken place. Okay, so that expansion must come at some cost. So it comes at the cost of the kinetic energy of the gas. So the temperature of the gas goes down and the gas is able to expand. So that is what basically its opposite is written here. Okay, total energy of the bubble will not change if the gas is a perfect heat insulator. The total energy will change. In fact, that total energy only is what will help us in expanding the gas. Option D is incorrect. So to close up this lecture, since we have been doing lots of questions, let us do some fun theory concept. So there is something which we discussed in this lecture, the first question. So that particular basically idea question, we discussed that if a ping pong ball is released with some speed, what will happen to its speed? So eventually, it will reach a terminal speed. So that speed with which it will go for infinite distance is a particular concept in physics actually. Well, it's the same speed with which raindrops fall on us. So let's see. So basically, the calculation is that let's say if a body is going with a speed v, there is a viscous force acting F, which we have known. There is a buoyant force acting on the body. So buoyant force will act in upward direction only. Let's say that is mv, and it's a gravitational force mg. So we want such a speed of this ball so that all these forces cancel out. So it's pretty easy to figure out, right? So this is the case when the body is going down, right? If the body were going up, right? In that case, the viscous force would be acting in the downward direction. So basically, what is the case with which we want? Um, so we want that the whatever force which we are applying, it is such that it is able to supply this band force and it is also able to balance this force F, right? Because this viscous force and the gravity or the band force, they are acting in the same direction.
So we'll have to balance both these forces. So there has to be some external force which is able to balance these forces. Let's say that external force is some, yes, because if we are applying some external force, then that would have been needed to balance this force F and this force F only. But we do not need that. We want the viscous force to balance the band force. So what we'll do is that we will say this force F is acting downwards and the ball is traveling upwards. So in that case, what will be the force F which will supply me the speed V so that all the forces cancel out? So we'll say 4 by 3 pi r cube density of the body, let's say it's some sigma. Oh yeah, rho density of the fluid is some sigma. So the band force is 4 by 3 pi r cube sigma g. That is equal to 4 by 3 pi r cube rho g. Rho is density of the body plus 6 pi r eta v. So this value again, these are equation that the gravitational force and the viscous force are being balanced by this band force. So we're pushing the body, so body is coming upwards automatically with the speed v, right? So this value v, it comes out to be 2 by 9 uh, r square g by eta sigma minus rho. So this rho sigma is called the density of the fluid, like I said. So this is the case when the fluid is uh, having higher density that than that of body. So when the fluid has a higher density, that means the body has very high band force. So it is automatically going up, and as it is automatically going up, so it is being opposed by that viscous force F, whose value we already know, 6 pi r beta v. So this is the terminal speed with which it reaches, and it is then just going on with that speed only. So that does not mean that all these forces will stop acting at that point. Viscous force F will act, band force will act, and gravitational force also will act. But we will say that uh, its speed will remain constant. So, like in the question which we discussed today, first question which we discussed, if we know what is the density of the body and we know what is the density of the water, which we know the density of water was some 10 to the power 3 kg per meter cube, and density of the body we can also figure out. Density of the body would be some, it would be some value. So after plugging those values here, I can find that terminal speed. So and that terminal speed I can put in that expression of 6 pi r beta v to get the maximum speed. And but that expression would be pretty close to the value 7 meter per second only. Because as we were calculating, that viscous force is pretty high. It is of the order 10 to the power 4. And the net force. And the viscous force is some of the order 10 to the power 1. So because of that, viscous force was almost negligible. So thank you for joining. Have a good day.